Gamma ray burst. You're monitoring the Swift gamma ray burst mission's data feed. September 16, 2008, Goddard Space Flight Center. The screens show routine background radiation. Then, everything changes. A signal tears through the detectors. The energy readings spike beyond the instrument's capacity. Your colleagues gather around the monitors. The numbers make no sense. This burst is coming from 12.2 billion light years away. It happened when the universe was less than 700 million years old. The light has been traveling toward Earth for most of cosmic history. What you're seeing destroyed everything within 6,500 light years of its source, in 23 seconds. The Swift Observatory's Burst Alert Telescope detected the initial gamma ray pulse at 14 hours, 12 minutes, and 19 seconds coordinated universal time. Within minutes, ground-based telescopes across 6 continents had swung toward the coordinates in the constellation Carina. The Gemini South Telescope in Chile, the Very Large Telescope in Chile's Atacama Desert, and the Hubble Space Telescope all locked onto the afterglow. What they found defied every model of stellar death. Gamma ray burst 080916C released approximately 10 to the 47th joules of energy. To comprehend this scale, our sun converts 4 million tons of matter into energy every second, following Einstein's mass energy equivalence. It has maintained this fusion rate for 4.6 billion years. It will continue for another 5 billion years. The total energy our sun will produce across its entire 10 billion year main sequence lifetime equals roughly 10 to the 34 joules. This single gamma ray burst, lasting 23 seconds, released over 1 trillion times more energy than our sun's complete existence. The burst originated from a galaxy designated as part of the Sloan Digital Sky Survey catalog, a faint smudge of light containing perhaps 100 billion stars. At a redshift of 4.35, the light began its journey when the universe contained only hydrogen, helium, and the first generation of massive stars. No planets existed. No complex chemistry had formed. The Milky Way was barely a collection of gas clouds beginning to collapse under gravity. Neil Gehrels, the Swift mission's principal investigator at Goddard, described the detection in the Astrophysical Journal in 2009. The paper documented how the burst's peak luminosity reached 10 to the 47 watts brighter than the combined light of every star in the observable universe for those 23 seconds. The X-ray afterglow remained detectable for months, slowly fading as the expanding shockwave swept through space at 99.9% the speed of light. The standard cosmological model explains gamma ray bursts as the collapse of massive stars into black holes. When a star exceeding 25 solar masses exhausts its nuclear fuel, its core implodes in microseconds. The collapsing matter forms an event horizon, while the outer layers rebound in a hypernova explosion. Magnetic fields, twisted and amplified during the collapse, channel twin jets of plasma along the star's rotation axis. These jets accelerate particles to near light speed, creating focused beams of gamma radiation. This model accounts for the basic mechanics. A hypernova's energy budget allows for gamma ray production. The beaming effect explains why we observe bursts as brief, intense flashes. We only see them when a jet points directly at Earth. The mathematical framework, developed by researchers including Stan Woosley at the University of California, Santa Cruz, and Andrew McFadyen at New York University, successfully predicts many observed properties of gamma ray bursts. But the sheer energy output of GRB 080916C exceeds what any known stellar collapse mechanism can produce. Even if you converted the entire mass of a 100 solar mass star directly into gamma radiation with perfect efficiency impossible under known physics, you would generate only 10 to the 45 joules. This burst required 100 times more energy than the complete annihilation of matter allows. Some astrophysicists suggest that magnetic field amplification during black hole formation could extract rotational energy from the collapsing core through the Blandford-Znayak mechanism. Others propose that the burst represents the formation of a magnetar, a neutron star, with magnetic fields trillions of times stronger than Earth's. A minority of researchers theorize about exotic matter phases or higher dimensional physics during stellar collapse. The Fermi Gamma Ray Space Telescope measured high-energy photons arriving from GRB 080916c with energies exceeding 33 billion electron volts, among the highest energy photons ever detected from any cosmic source. These photons should have been absorbed by interactions with infrared background light during their 12 billion year journey through space. Yet they reached our detectors. Where does a star find energy exceeding the total mass energy conversion of 100 suns? How do photons travel 12 billion light years without absorption? What mechanism focuses this incomprehensible violence into beams narrow enough to appear as 23-second flashes? If such an event occurred within 6,000 light years of Earth, would our atmosphere survive the gamma ray sterilization? The universe's capacity for destruction operates on scales that make terrestrial catastrophes seem gentle, and sometimes that destruction announces itself through much smaller but equally mysterious events closer to home. The Carrington event. You are hunched over a telegraph key in Boston, September 2nd, 1859, 2 in the morning. The brass instrument sparks under your fingertips. Every line across North America has been dead for hours. You disconnect the battery, the key shouldn't work. Yet somehow, impossibly, your message continues transmitting across 1,000 miles of copper wire, powered by something flowing down from the aurora-painted sky above. The most powerful geomagnetic storm in recorded history began 35 hours earlier when British astronomer Richard Carrington observed two brilliant white light flares erupting from a cluster of sunspots through his 8-inch refractor telescope at his private observatory in Red Hill, Surrey. The Solar and Heliospheric Observatory would later determine that coronal mass ejections of this magnitude released the energy equivalent of 10 billion atomic bombs every second for several hours. Carrington's sketches, published in the monthly notices of the Royal Astronomical Society in 1860, document plasma traveling from the sun to Earth in just 17 hours. Normal solar wind takes 3 to 4 days to make this journey of 93 million miles. Telegraph networks across Europe and North America collapsed within minutes of the storm's arrival. The induced electrical currents flowing through the wires measured over 1 ampere in some locations. Telegraph operator reports from September 1st through 2nd, archived by the Smithsonian Institution, describe sparks jumping from equipment, fires igniting in telegraph offices from New York to Stockholm, and operators receiving electric shocks that threw them across rooms. But here's what makes this impossible. Dozens of documented cases exist of telegraph systems continuing to operate for hours after their power sources were completely disconnected. The electromagnetic field fluctuations were generating sufficient current to power the entire continental telegraph network. The aurora displays reached latitudes never recorded before or since. Eyewitness accounts published in newspapers from Honolulu to Rome describe crimson and green curtains of light bright enough to read by at midnight. Gold miners in the Rocky Mountains woke thinking it was dawn. Ships' captains in the Caribbean logged northern lights stretching across the entire horizon. The geomagnetic disturbance was so intense that compass readings shifted by as much as 7 degrees across the continental United States. The standard solar physics model explains the Carrington event as an exceptionally powerful but fundamentally normal coronal mass ejection. When magnetic field lines in the sun's corona suddenly reconnect, they accelerate charged particles to velocities approaching 10,000 kilometers per second. These particles, upon reaching Earth's magnetosphere, compress and distort our planet's magnetic field, inducing electrical currents in any conducting material, including telegraph wires and railroad tracks. The unprecedented intensity resulted from the perfect alignment of the ejection's magnetic field with Earth's magnetosphere, allowing maximum energy transfer. But the model cannot account for the sustained power generation after electrical disconnection. Standard electromagnetic induction requires a changing magnetic field to produce current flow. Once telegraph batteries were removed, the circuits should have gone dead within seconds as the stored energy dissipated. Instead, operators continued sending messages for hours. The transcontinental telegraph line between New York and San Francisco operated entirely on storm-induced power for over 2 hours. This suggests the geomagnetic disturbance was creating some form of continuous energy coupling between the Earth's magnetic field and the copper wire networks that current physics cannot fully explain. Some space physicists suggest the storm created temporary superconducting conditions in the telegraph infrastructure. The extreme magnetic field fluctuations may have altered the electrical properties of copper wire over continental distances. Others propose that the interaction between the solar particle stream and Earth's ionosphere generated a form of atmospheric electrical gradient that could sustain current flow through grounded networks. The phenomenon has never been successfully reproduced or adequately modeled. Modern analysis of ice core samples from Greenland indicates the Carrington event deposited nitrates at concentrations 60% higher than any other solar storm in the past 4 centuries. The Goddard Space Flight Center estimates that a similar event today would cause $2 trillion in damage to satellite networks, power grids, and communication systems. GPS satellites would be blinded. The internet would collapse across entire continents. Yet questions remain that no solar model addresses completely. How did an electromagnetic disturbance generate sustained electrical power without any conventional energy source? Why has no subsequent solar storm, including the 1989 Quebec blackout, demonstrated this same phenomenon of power generation? What specific conditions during the Carrington event created effects that our current understanding of electromagnetism says should be impossible? Could such an event trigger cascading failures that would disable every electronic system on Earth simultaneously? The next time we turn our attention skyward, we're looking towards something far more permanent and far more dangerous than any solar storm. Sagittarius A star. You are monitoring the Event Horizon Telescope data stream from the Atacama Large Millimeter Array in Chile, March 15, 2022. 347 terabytes of observational data flowing through fiber optic cables at your workstation. The radio waves began their journey 26,000 light years ago, when early humans were painting caves in Europe. Now they paint a portrait of something that shouldn't be so quiet. The supermassive black hole at the center of our galaxy weighs 4.1 million times more than our sun. It sits there, 26,000 light years away, barely feeding. But the simulations running on your screen show what happens if it wakes up hungry. Earth's atmosphere begins stripping away in the models. From 26,000 light years away, you watch our planet's protective shell peeling into space like paint in a cosmic wind. This is Sagittarius A star, and it's been remarkably, inexplicably dormant. The Keck Observatory first detected stars orbiting this invisible gravitational anchor in 1995. Reinhard Genzel and Andrea Ghez tracked stellar object S2, completing a 16-year elliptical orbit around empty space, reaching speeds of 7,650 kilometers per second at closest approach. Their Nobel Prize-winning observations prove that 4.1 million solar masses of matter occupy a region smaller than our solar system. The European Southern Observatory's Very Large Telescope confirmed the orbital mechanics. The Event Horizon Telescope collaboration published the first direct image in 2022, showing the shadow of the event horizon surrounded by superheated plasma glowing at 100 billion Kelvin. The measurements are precise. The mass is contained within the Schwarzschild radius. This is a supermassive black hole. Here's what makes this impossible to ignore. When supermassive black holes feed actively, they become quasars, the most luminous objects in the universe. Matter spiraling into the accretion disk heats to temperatures exceeding 1 trillion Kelvin, producing energy output that can be seen from billions of light years away. The nearest quasar, 3C273, sits 2.4 billion light years from Earth and outshines entire galaxy clusters. Its central black hole masses roughly 1 billion times our sun. Sagittarius A star could theoretically match this energy output if it began accreting material at maximum efficiency. The radiation pressure alone would strip planetary atmospheres throughout the galaxy's inner regions. High-energy gamma rays and X-rays would sterilize any worlds within 50,000 light years. Our solar system sits well within this kill zone. The standard cosmological model says supermassive black holes experience periods of active feeding, followed by dormant phases, lasting millions of years. Sagittarius A star appears to be in a quiet state, consuming roughly 1 Earth mass of material every million years. Computer simulations from the Max Planck Institute for Astrophysics show that molecular gas clouds regularly pass near the galactic center. Most of this material gets heated and dispersed by stellar winds before reaching the accretion disk. The black hole's current luminosity measures only 1/billionth of what it would produce during active feeding. This dormant state explains why our galaxy's central region remains relatively stable and why complex life could evolve in the galactic disk. But the observational data reveals troubling inconsistencies. The Chandra X-ray Observatory detected massive gas clouds approaching Sagittarius A star with unusual density concentrations. Cloud G2 passed within 120 astronomical units of the event horizon in 2014. Theoretical models predicted dramatic brightening as the cloud's material fed the black hole. Instead, the system remained quiet. The cloud passed by virtually unaffected. Some astrophysicists suggest that G2 was actually a young star surrounded by an extended gas envelope, explaining its survival. Others propose that the black hole's magnetic field configuration prevents efficient accretion of diffuse material. Neither explanation addresses why such a massive gravitational system shows so little feeding activity compared to other galactic centers. Radio observations from the Atacama Large Millimeter Array reveal periodic flare events lasting several hours. These brief brightenings increase the black hole's luminosity by factors of 10 to 100 before returning to baseline levels. The flares occur randomly, sometimes multiple times per day, sometimes with months between events. The mechanism driving these variations remains unexplained. Magnetohydrodynamic simulations cannot reproduce the observed flare patterns. The relationship between stellar orbits, gas dynamics, and accretion efficiency around Sagittarius A star defies current theoretical frameworks. Why does a 4 million solar mass black hole consume so little material when surrounded by stars and gas clouds? What triggers the random flare events that briefly illuminate our galaxy's center? Could external factors suddenly drive Sagittarius A star into an active feeding state? How quickly would the transition from dormant to active quasar phase strip away Earth's atmosphere? What early warning systems could detect the onset of catastrophic feeding activity 26,000 light-years away? The next cosmic threat operates on a much shorter timescale, positioned just 650 light-years from our solar system, where a red supergiant star approaches the final moments of its stellar evolution. Betelgeuse. You are staring at Orion's shoulder through the Hubble Space Telescope's imaging system on a December night in 2020. The red supergiant that has anchored this constellation for millennia appears 30% dimmer than it did just months ago. The photometric data streaming across your monitor shows something that makes veteran astronomers pause mid-conversation. Betelgeuse is flickering. Not the gentle variability of a normal star, but erratic, unpredictable dimming that suggests the internal structure of a star 648 light-years away is becoming fundamentally unstable. The European Southern Observatory's Very Large Telescope confirmed what ground-based observers had been tracking since late 2019. Betelgeuse had dimmed by more than 1 full magnitude, dropping from its usual brightness of 0.5 to nearly 1.7. For a star that typically varies by only a few tenths of a magnitude over its 425-day pulsation cycle, this represented a dramatic departure from normal behavior. The star's effective temperature had dropped by roughly 160 Kelvin. Its radius had contracted by 15%. Something fundamental was happening inside this stellar giant that contains enough mass to create 6,400 Earths. Spectroscopic analysis from the Atacama Large Millimeter Array revealed the presence of silicon monoxide and aluminum oxide in Betelgeuse's outer atmosphere, molecular signatures that form only when stellar material cools to specific temperatures. The star was literally ejecting parts of itself into space at velocities exceeding 30 kilometers per second. Follow-up observations by the Stratospheric Observatory for Infrared Astronomy detected infrared signatures consistent with dust formation in the star's immediate vicinity, confirming that Betelgeuse was shedding material at an unprecedented rate. Dr. Emily Levesque's research at the University of Washington published in the Astrophysical Journal in 2021, cataloged the observational signatures that precede core collapse supernovae in red supergiants. Betelgeuse exhibited 7 of the 9 documented pre-explosion indicators. The star's core temperature had likely reached 1 billion Kelvin, hot enough to begin silicon burning, the final nuclear fusion process before gravitational collapse. Models suggest that once silicon burning begins, a star of Betelgeuse's mass has between days and decades before its core can no longer support itself against gravity. Here's what makes this terrifying. When Betelgeuse explodes, it will release more energy in 10 seconds than our sun will produce over its entire 10 billion year lifespan. The explosion will be visible during daylight on Earth, potentially outshining the full moon for weeks. But the electromagnetic radiation represents only the beginning of what Earth would experience. The standard stellar evolution model says that red supergiants like Betelgeuse undergo core collapse when iron accumulates in their cores, to the point where nuclear fusion can no longer counteract gravitational compression. The core collapses from the size of Earth to a neutron star 20 kilometers across in less than 1 second. The resulting shock wave tears through the star's outer layers, creating a Type II supernova that disperses heavy elements throughout the surrounding interstellar medium. At 648 light-years distance, Betelgeuse poses no immediate threat to Earth's biosphere. But recent modeling by Dr. Adrian Melot's team at the University of Kansas suggests something far more concerning. Their work, published in Astrobiology in 2018, indicates that supernovae within 1,000 light-years of Earth can significantly deplete the ozone layer through gamma-ray and X-ray bombardment. Betelgeuse sits well within this danger zone. The initial gamma-ray burst would reach Earth approximately 648 years after the explosion occurs, carrying enough high-energy radiation to strip away between 20 and 60% of Earth's ozone layer within months. The ozone depletion would persist for years, allowing lethal levels of ultraviolet radiation to reach Earth's surface. Marine ecosystems would collapse as phytoplankton, the foundation of ocean food chains, died en masse. Agricultural systems would fail as crops suffered radiation damage. The increased cancer rates among surface-dwelling organisms would trigger mass extinctions, comparable to the Ordovician-Silurian event 445 million years ago. Some astrophysicists suggest that Betelgeuse's recent dimming episode was merely an unusually large convective event, where hot material from the star's interior rose to the surface and cooled, temporarily reducing the star's brightness. They point to the star's return to normal brightness by mid-2020 as evidence that the dimming represented normal, if extreme, stellar variability rather than pre-supernova behavior. Yet the spectroscopic signatures remain unexplained. Why did Betelgeuse eject so much material during the dimming event? What triggered such massive convective instabilities? How can models account for the rapid temperature and radius changes observed across multiple wavelengths? The star continues to show irregular brightness variations that deviate from its established pulsation pattern. Could Betelgeuse explode tomorrow? Or will it remain stable for another 100,000 years? Would Earth's magnetic field provide any protection against the gamma-ray bombardment? How quickly would the ozone layer recover after such an assault? Can civilization prepare for an extinction-level event that might occur at any moment across geological timescales? What does it mean that our species' survival depends partly on the internal nuclear processes of a star visible to the naked eye? Perhaps what's most unsettling is that Betelgeuse exists within a region of space where massive stars have already shaped the local cosmic environment in ways we're only beginning to understand. The local bubble. You are standing in your backyard, looking up at the Milky Way on a clear night. The stars seem eternal, fixed, safe. You cannot see what astronomers have mapped around you, a hollow sphere of near vacuum 300 light-years across, carved by stellar explosions that detonated when your ancestors were still learning to walk upright. You are floating inside a cosmic cavity, surrounded by walls of superheated gas at 1 million Kelvin, protected only by a magnetic field that fluctuates like a candle flame in the wind. The Hipparcos satellite first mapped the local bubble's boundaries in 1997. Then the Gaia Space Telescope refined the measurements between 2016 and 2022. The European Space Agency's data revealed the precise architecture of our cosmic neighborhood. We sit inside an enormous cavity blown clear by a chain of supernovae that exploded between 10 and 20 million years ago. The local group of stars, including our sun, drifts through this hollow region at 26 kilometers per second. The cavity extends roughly 150 light years in every direction, though the shape is irregular, bulging toward the constellation Centaurus and compressed near the Aquila Rift. Beyond these boundaries lies the local bubble wall, detected by the Far Ultraviolet Spectroscopic Explorer and confirmed by the Chandra X-ray Observatory. This shell consists of shocked interstellar medium heated to temperatures between 500,000 and 1 million Kelvin. The wall glows in soft X-rays, invisible to human eyes but blazing bright to space-based detectors. Harvard-Smithsonian Center for Astrophysics researchers led by Catherine Zucker published findings in Nature in 2022, mapping the three-dimensional structure using dust extinction measurements. Their data showed that at least 15 supernovae exploded in our region over the past 20 million years, each blast wave sweeping away interstellar gas and dust, creating this vast bubble of near-empty space. The local bubble contains only 0.01 solar masses of material per cubic parsec, 10,000 times less dense than typical interstellar medium. Here's what makes this dangerous. The sparse material inside the local bubble provides minimal shielding against cosmic radiation. Galactic cosmic rays, high-energy particles accelerated by distant supernovae, and stellar processes stream through this cavity with little obstruction. Earth's heliosphere, the magnetic bubble generated by our sun's solar wind, extends roughly 100 astronomical units outward. Beyond that boundary, we rely on the interstellar medium to absorb and deflect incoming radiation. The standard astrophysical model says this sparse environment poses minimal immediate threat to Earth. Our planet's magnetic field deflects most charged particles. The atmosphere absorbs remaining radiation. The heliosphere provides additional protection within the inner solar system. Regional variations in cosmic ray intensity, while measurable, fall within ranges that complex life has survived for hundreds of millions of years. But the local bubble structure suggests more violent events may be coming. Stellar kinematics data from Gaia shows the Upper Centaurus Lupus Association, a group of young, massive stars sitting near the local bubble's edge. These stars formed from the same material ejected by the original supernova chain. Several of these stars, including ones with masses 20 to 30 times that of our sun, will explode within the next few million years. University of Chicago astrophysicist Priscilla Frisch, who has studied the local bubble since the 1980s, notes that Earth has been moving through this cavity for the past 5 to 10 million years. During this time, cosmic ray flux at Earth's position has varied significantly as we encounter different regions of the bubble wall. Paleoclimate data shows correlations between cosmic ray intensity and cloud formation, potentially linking our passage through the local bubble to ice age cycles. Some researchers suggest that our current position near the bubble's center provides temporary protection, but this safety is not permanent. As the solar system continues its orbit around the galactic center, we will eventually approach the bubble wall, where cosmic ray intensity increases dramatically. Radio astronomy surveys using the Very Large Array have detected shocked gas regions where the bubble interacts with surrounding molecular clouds, creating zones of enhanced radiation. The most unsettling possibility involves the bubble's future evolution. Computer simulations run by researchers at the Max Planck Institute for Astronomy predict that additional supernovae from the Upper Centaurus Lupus Association could merge our local bubble with adjacent cavities, creating a superbubble structure. Such events have been observed in other galaxies using the Hubble Space Telescope. These merged cavities can extend over 1,000 light years across, with walls so hot they emit gamma rays. What happens when the next supernova detonates in our stellar neighborhood? How much cosmic radiation can Earth's biosphere absorb before complex life begins to fail? Could the local bubble's evolution trigger another mass extinction event? Are we living through a temporary period of cosmic calm between much more dangerous episodes. Why does life on Earth seem to have emerged during one of the galaxy's most violent periods of local star formation? The question of cosmic threats extends beyond distant explosions to objects much closer to home, including asteroids whose orbits occasionally intersect our own. Apophis. You are staring at a computer screen in the Jet Propulsion Laboratory in Pasadena, California. The date is June 19th, 2004. The numbers cascading down your monitor represent the orbital trajectory of asteroid 2004 MN4, a 370-meter wide chunk of rock and metal currently hurtling through space at 28,000 kilometers per hour. You run the calculations again. The asteroid will pass within 31,300 kilometers of Earth on April 13th, 2029. Your hands freeze over the keyboard. Geostationary satellites orbit at 35,786 kilometers. This rock will pass closer to Earth than our television satellites. The Arecibo Observatory and the Goldstone Deep Space Communications Complex have been tracking this object since its discovery by Roy Tucker, David Tholen, and Fabrizio Bernardi at the Kitt Peak National Observatory. Named Apophis, after the ancient Egyptian serpent god of chaos and destruction, this near-Earth asteroid belongs to the Aten group objects whose orbits cross Earth's path around the Sunday. Spectroscopic analysis reveals an SQ-class composition, a mixture of silicate rock and metallic iron nickel, dense enough to survive atmospheric entry largely intact. Here's what makes this encounter unprecedented. Apophis will approach Earth closer than any asteroid of its size in recorded human history. On that April afternoon in 2029, observers in Europe, Africa, and Western Asia will watch with naked eyes as a star-like point of light streaks across the sky, visible in broad daylight. The asteroid will experience tidal forces from Earth's gravity approximately 250 times stronger than its own surface gravity. These forces will literally reshape the asteroid, potentially triggering landslides, structural collapse, and the shedding of surface material. The gravitational interaction works both ways. Earth's gravity will bend Apophis's trajectory by 28 degrees, fundamentally altering its future orbit around the Sunday. But the precise degree of deflection depends on variables we cannot measure with absolute certainty. The asteroid's exact mass distribution, its internal structure, its rotation state, and the Yarkovsky effect, the tiny but persistent push created when the asteroid absorbs sunlight and re-radiates it as heat. The mainstream scientific consensus is that Apophis poses no immediate collision threat. Radar observations from Arecibo and Goldstone, combined with optical tracking from observatories worldwide, have refined the asteroid's orbit to within kilometers. The European Space Agency's Hera mission and Japan's Hayabusa 2 have demonstrated our ability to precisely map asteroid trajectories years in advance. Computer models show Apophis passing safely by Earth with zero probability of impact during the 2029 encounter. But the data reveals something more unsettling. The 2029 flyby will thread Apophis through gravitational keyholes, narrow regions of space where Earth's gravity could deflect the asteroid onto a collision course for future encounters. These keyholes are typically only a few hundred meters wide, but if Apophis passes through one, it could return to strike Earth on April 13th, 2036, or 2068, or on subsequent orbital returns. The asteroid's trajectory depends on factors measured in centimeters and grams. A difference of just 60 centimeters in Apophis's position during the 2029 flyby could determine whether it misses Earth entirely or returns as a planet killer. The Yarkovsky effect alone could shift the asteroid's path by more than 100 kilometers over the next decade. Surface composition variations, invisible to current telescopes, could alter its thermal properties and change its trajectory by unpredictable amounts. Some planetary defense researchers propose active deflection missions. The Double Asteroid Redirection Test mission successfully demonstrated kinetic impactor technology in 2022, shifting the orbit of asteroid Dimorphos by 32 minutes. But Apophis presents a different challenge. Any deflection attempt would need to occur years before the 2029 encounter to avoid pushing the asteroid into a keyhole rather than away from one. The European Space Agency's proposed Ramses mission would rendezvous with Apophis before the encounter to study how Earth's gravity reshapes the asteroid in real time. The physics are straightforward, but the uncertainties compound exponentially. Each measurement error, each unknown variable in the asteroid's composition and structure, each tiny force acting on the rock over 25 years propagates into meters or kilometers of uncertainty in its final trajectory. We are tracking a bullet fired a quarter century ago, trying to predict where it will be when it reaches us. What happens if our measurements are wrong by just a few meters? What forces might we have overlooked that could nudge Apophis into a keyhole trajectory? How do we defend against a threat that depends on variables we cannot directly observe? Can we trust models that depend on measurements at the very limit of our instrumental precision? How many other asteroids are threading similar gravitational needles without our knowledge? The 2029 encounter is just the beginning, but Earth itself harbors anomalies that could prove equally threatening to our technological civilization. The South Atlantic anomaly. You are monitoring the International Space Station's orbital telemetry from Mission Control Houston when the radiation alerts begin cascading across your screens. March 15th, 2023, the station is passing over Brazil at 408 kilometers altitude. Every sensitive instrument aboard is registering particle bombardment levels that should be impossible at this orbital height. The crew reports computer glitches, navigation systems stutter. The solar panels are detecting charged particle impacts at rates typically seen only during major solar storms. But there is no solar storm. The sun is quiet. What you are witnessing is the International Space Station passing through a region of space where Earth's protective magnetic field has weakened so dramatically that the boundary between our planet's magnetosphere, hostile radiation environment of space has effectively collapsed. The European Space Agency's Swarm constellation, launched in November 2013, has been mapping Earth's magnetic field with unprecedented precision for over a decade. The data reveals a disturbing pattern. Over South America and the southern Atlantic Ocean, extending across parts of southern Africa, the magnetic field strength has decreased by approximately 5% per decade since the 1970s. The region, known as the South Atlantic Anomaly, now covers an area roughly the size of the continental United States. Within this zone, the magnetic field intensity measures between 24,000 and 32,000 nanotesla, compared to the global average of approximately 50,000 nanotesla. Satellites passing through this region experience radiation doses equivalent to what they would normally encounter during their entire operational lifetime, compressed into minutes. Dr. Jürgen Matzke of the German Research Center for Geosciences published findings in Earth, Planets, and Space in 2021 documenting the anomaly's expansion. The weakened field allows charged particles from the Van Allen radiation belts to penetrate deeper into Earth's atmosphere. At aircraft cruising altitudes over the anomaly, radiation exposure rates reach levels comparable to those experienced by astronauts on the International Space Station. Commercial airlines have begun rerouting flights to avoid the most severely affected regions during periods of elevated solar activity. The magnetic field originates from convection currents in Earth's liquid iron outer core, located between 2,900 and 5,150 kilometers below the surface. Computer models developed by the University of Rochester suggest that a massive blob of dense rock sitting at the core mantle boundary beneath southern Africa is disrupting the normal flow patterns that generate the magnetic field. This structure, detected through seismic tomography, appears to be affecting the convection currents responsible for generating the geomagnetic field lines that normally deflect harmful solar wind particles away from Earth's surface. The standard geophysical model says magnetic field variations are normal features of Earth's dynamic core processes. The planet has experienced numerous magnetic pole reversals throughout geological history, with the most recent occurring approximately 770,000 years ago. During these transitions, the magnetic field strength decreases significantly before reorganizing with opposite polarity. Computer simulations indicate that the South Atlantic anomaly represents an early stage of a potential pole reversal process that could take several thousand years to complete. But the current rate of weakening is unprecedented in the observational record. Paleomagnetic data from volcanic rocks and deep-sea sediments indicates that previous magnetic transitions occurred over timescales of thousands to tens of thousands of years. The South Atlantic anomaly is intensifying and expanding at a rate that suggests a complete local collapse of magnetic protection could occur within centuries rather than millennia. Some geophysicists suggest that the anomaly represents not a gradual pole reversal, but a fundamental instability in Earth's magnetic dynamo that could lead to a prolonged period of extremely weak or absent magnetic field protection. Ground-based measurements from the Hermanus Magnetic Observatory in South Africa show that local magnetic field strength in some regions of the anomaly has decreased by over 10% since 2000. The European Space Agency's Alpha Magnetic Spectrometer data indicates that cosmic ray penetration through the anomaly has increased by corresponding amounts. At current rates of decline, portions of the South American continent could lose effective magnetic shielding within 2 to 3 centuries. The implications extend beyond increased radiation exposure. Earth's magnetic field protects not only biological systems, but also the technological infrastructure that modern civilization depends upon. Power grids, satellite communications, and GPS navigation systems all rely on magnetic field stability. A continued expansion and deepening of the South Atlantic anomaly could render vast regions of the planet uninhabitable while simultaneously crippling global communications and navigation networks. What happens when a planet's magnetic shield fails completely? Could the anomaly trigger a cascade collapse of the entire magnetosphere? How long can complex life survive under direct cosmic ray bombardment? Are we witnessing the beginning of Earth's transformation into a magnetically dead world like Mars? The universe contains forces capable of unmaking reality itself at the quantum level. False vacuum decay. You're staring at equations that describe the end of everything. The numbers glow on your monitor in the theoretical physics department at CERN, Switzerland. It's 2:37 in the morning, October 15th, 2023. The calculations are elegant, beautiful, terrifying. They suggest our entire universe exists in a state physicists call false vacuum, a quantum field configuration that appears stable but isn't, like a ball balanced on a hill that looks flat but contains an invisible slope. One quantum fluctuation, one random event. The ball rolls, reality collapses. Everything that has ever existed or ever could exist gets erased at exactly 299,792,458 meters per second. The speed of light, you cannot outrun it. You cannot hide from it. You cannot detect it coming. The Higgs field discovery at the Large Hadron Collider in 2012 changed everything physicists thought they knew about vacuum stability. Peter Higgs and Francois Englert had predicted this fundamental field in 1964, but when the particle accelerator finally detected the Higgs boson at 125 billion electron volts, the measurements revealed something unsettling. The mass of the Higgs boson sits right at the edge of metastability. If the field exists in what quantum field theorists call a false vacuum state, our universe represents just one possible configuration of quantum fields. Not the lowest energy state, not true vacuum, a temporary arrangement that could collapse without warning. Here's what makes this impossible to accept. The false vacuum scenario suggests every atom, every molecule, every fundamental particle exists only because quantum fields haven't yet found their ground state. Sidney Coleman at Harvard University published the foundational work on vacuum decay in 1977, demonstrating mathematically how a universe in false vacuum could spontaneously tunnel to true vacuum through pure quantum mechanics. No external trigger required. No advanced warning possible. The collapse begins at a single point and expands outward at light speed, creating a bubble of true vacuum that converts every particle it encounters into the lowest possible energy configuration. Joseph Licken at Fermilab in the University of Chicago calculated the current metastability parameters in 2012 using precise measurements from the Large Hadron Collider. The Higgs field sits in a local minimum, not the global minimum. Like water that should be ice but hasn't frozen yet, supercooled, unstable. The barrier between our current state and true vacuum measures approximately 10 to the 16th billion electron volts, enormous by particle physics standards. But quantum mechanics allows tunneling through any barrier given sufficient time. The lifetime calculations span ranges that make geological time look instantaneous. Conservative estimates suggest our false vacuum could persist for 10 to the 100 years before spontaneous decay becomes likely. Far longer than the current age of the universe at 13.8 billion years. The probability remains vanishingly small across human timescales. Some theoretical physicists, including Stephen Hawking before his death in 2018, argued that cosmic inflation in the early universe would have driven any metastable vacuum fields to their true ground states billions of years ago. The standard cosmological model says false vacuum decay represents no immediate threat to Earth or human civilization. The timescales involved exceed the lifespan of stars, galaxies, and possibly the observable universe itself. Even if decay occurred, the expanding bubble of true vacuum would be undetectable until the moment of arrival. No electromagnetic signature, no gravitational wave emission, no advance warning of any kind. Death would be instantaneous and absolute. Every atomic nucleus would dissolve, every chemical bond would break, every quantum field would reset to its lowest energy state. The bubble interior would contain no atoms, no molecules, no matter as currently understood. But quantum field theory contains fundamental uncertainties about vacuum stability that no experiment can resolve completely. The precise shape of the Higgs potential depends on measurements of particle masses and coupling constants that carry experimental uncertainty. Small changes in these values could shift the metastability calculation dramatically. Some physicists propose that high-energy cosmic ray interactions, or artificial particle accelerator experiments, could catalyze vacuum decay by providing sufficient local energy to overcome the barrier between false and true vacuum states. Alan Guth at the Massachusetts Institute of Technology has argued that vacuum decay could already be occurring somewhere in the infinite multiverse implied by cosmic inflation theory. If our observable universe represents just one bubble in an eternally inflating cosmological structure, other regions could be experiencing false vacuum collapse right now. The bubble walls would expand at light speed, eventually reaching our local region of space-time. No detection possible, no escape route available. Just the universe changing the rules of physics faster than information can travel. Would we detect the approach of a vacuum decay bubble before it reached Earth? Could high-energy particle physics experiments accidentally trigger the collapse they study? Does the metastability of our quantum vacuum suggest we exist in one of countless temporary realities? How long can false vacuum persist when quantum mechanics guarantees that anything possible will eventually occur? But terrestrial catastrophes require no quantum field collapse to threaten human survival, as evidenced by the massive magma chamber currently building pressure beneath Wyoming's most famous national park, Yellowstone supervolcano. You are monitoring seismic sensors across the Yellowstone Plateau on a routine Tuesday morning in March. The readouts from the University of Utah seismograph stations show the familiar background tremor. Ground deformation measurements from the Yellowstone Volcano Observatory indicate the caldera floor has risen 3 centimeters since last year. Hot springs are registering temperatures 40 degrees above normal. Everything appears stable. Everything appears manageable. Then you examine the geological timeline. 640,000 years ago, the Yellowstone caldera erupted with a force that ejected 1,000 cubic kilometers of material into the atmosphere. The explosion was heard across half the continent. Ash fell as far as the Gulf of Mexico. The eruption created a caldera 45 kilometers long and 85 kilometers wide that still defines the landscape today. This was the most recent of 3 supereruptions that have occurred at roughly 600,000-year intervals over the past 2 million years. The Huckleberry Ridge eruption occurred 2.1 million years ago. The Mesa Falls eruption happened 1.3 million years ago. The Lava Creek eruption happened 640,000 years ago. Each separated by approximately 650,000 years, each progressively moving northeast along the track of the North American plate over the Yellowstone hotspot. Ground-penetrating radar and seismic tomography conducted by the United States Geological Survey have mapped the magma chamber beneath Yellowstone. The primary chamber extends 64 kilometers long, 40 kilometers wide, and 8 kilometers deep. It sits just 6 to 8 kilometers below the surface. Temperature measurements indicate the magma reaches 1,200 degrees Celsius. The chamber contains an estimated 15,000 cubic kilometers of partially molten rock. The magma composition analysis published in the Journal of Petrology in 2021 shows rhyolitic magma with 72% silica content. High silica content creates explosive eruptions. The dissolved gas pressure within this magma system approaches critical thresholds observed before historical supereruptions. The standard volcanological model explains supervolcanoes as products of deep mantle hotspots. The Yellowstone hotspot originates from a thermal plume rising from the core mantle boundary 2,900 kilometers below the surface. As the North American plate moves southwest at 4 centimeters per year, the hotspot burns through the crust, creating the track of calderas from the Snake River Plain to Yellowstone. The model predicts periodic eruptions as pressure builds and releases in the crustal magma system. Seismic monitoring shows continuous earthquake swarms beneath the caldera. Ground deformation measurements indicate the caldera floor rises and falls in cycles lasting decades. Gas emissions from hot springs contain elevated levels of carbon dioxide and hydrogen sulfide, consistent with active magma degassing. These patterns match pre-eruption signatures observed at other large volcanic systems worldwide. But the temporal precision challenges current understanding of volcanic cycles. Supervolcanoes typically show irregular eruption intervals spanning hundreds of thousands of years. The Yellowstone system demonstrates remarkable periodicity over 2 million years. Each major eruption occurs within 50,000 years of 600,000-year intervals. This consistency suggests a driving mechanism more regular than the chaotic convection patterns typically associated with mantle plumes. Recent magnetotelluric surveys published in Nature Geoscience in 2022 reveal a second, deeper magma reservoir extending from 20 to 50 kilometers depth. This reservoir contains an estimated 30,000 cubic kilometers of partially molten rock. The connection between the upper and lower chambers shows complex dynamics that current models cannot fully predict. Some volcanologists propose that the Yellowstone system operates on a pressure release cycle driven by the interaction between the deep hotspot and the moving continental plate. The regular spacing of eruptions might result from predictable stress accumulation as the plate moves across a stationary thermal anomaly. Others suggest external triggers, including glacial loading cycles or changes in regional stress fields, could synchronize the eruption timing. The geochemical analysis of past eruptions shows increasing explosive potential over the 2 million year cycle. Each successive eruption has produced more silicic magma with higher gas content. The trend suggests the next eruption could exceed the scale of previous events. Is the 640,000 year gap since the last eruption approaching a critical threshold? Does the remarkable periodicity of past eruptions indicate an overdue event? Why does the Yellowstone system show such temporal regularity when other supervolcanoes remain chaotic? Could the increasing explosive potential of successive eruptions mean the next event will be unprecedented? What forces maintain such precise timing across geological timescales? While terrestrial supervolcanoes operate on timescales measured in hundreds of thousands of years, the cosmos contains stellar phenomena that can sterilize entire regions of space in mere seconds. Eta Carinae binary system. You stand in the control room of the Hubble Space Telescope Operations Center on a January morning in 2023, watching data stream across multiple monitors. The infrared sensors are tracking something 7,500 light years away in the constellation Carina. Two massive stars, locked in a death spiral, bleeding plasma into space at rates that defy comprehension. The larger star weighs 100 solar masses. Its companion weighs 50. Together, they represent enough nuclear fuel to outshine our entire galaxy for weeks. The system has been unstable for centuries, erupting periodically with the force of 1,000 supernovae. And now, the orbital decay models show something that makes veteran astronomers step back from their screens. The binary system is accelerating toward a collision that could produce the most violent explosion in the observable universe. Here's what makes this impossible. Eta Carinae is already the most luminous star system ever directly observed. The European Southern Observatory's Very Large Telescope has tracked its luminosity at 5 million times brighter than our sun day. During its 1840s Great Eruption, cataloged by astronomer John Herschel from the Cape of Good Hope, the system briefly became the second brightest star in Earth's sky, visible during daylight hours, despite being 7,500 light-years distant. The Spitzer Space Telescope's infrared observations, published in the Astrophysical Journal in 2014, reveal a nebula of ejected material stretching over 10 light-years across, containing debris equivalent to 20 solar masses. The system is losing mass at a rate of 1 Earth mass every 40 days. No known stellar physics can sustain this level of energy output without immediate gravitational collapse. The Hubble Space Telescope's Treasury Program for Eta Carinae, led by principal investigator Chris Davidson of the University of Minnesota, has documented spectroscopic evidence of helium and nitrogen emission lines moving at velocities exceeding 700 kilometers per second. The system's X-ray emissions, measured by the Chandra X-ray Observatory, fluctuate on a 5.5-year cycle, indicating orbital mechanics between two objects of extraordinary mass. Radio observations from the Australia Telescope Compact Array show expanding shock fronts in the surrounding nebula, moving at speeds approaching 1% the speed of light. The combined luminosity output suggests nuclear fusion rates 10 million times more intense than the sun's core. Dr. Roberta Humphreys of the University of Minnesota, leading researcher on luminous blue variables, has calculated that Eta Carinae contains enough hydrogen fuel to sustain current energy output for only 10,000 more years, a cosmically brief moment. The system's Eddington limit, the theoretical maximum luminosity before radiation pressure overcomes gravitational binding, has been exceeded by factors of 10. Ground-based observations from Cerro Tololo Inter-American Observatory show periodic dimming events lasting months, suggesting massive stellar winds creating dust clouds dense enough to obscure starlight across interstellar distances. The standard cosmological model says that stars exceeding 100 solar masses cannot exist in the current universe. The primordial stellar population, formed from pure hydrogen and helium in the early cosmos, could theoretically reach such masses, but no mechanism allows for their formation in metal-rich environments like the Milky Way's spiral arms. Stellar evolution theory predicts that objects this massive should undergo core collapse within 1 million years of formation, far too brief a timescale to allow the complex orbital dynamics observed in Eta Carinae. The system should have destroyed itself long before developing its characteristic bipolar nebula structure. But the observational evidence contradicts every theoretical framework. Some astrophysicists suggest that Eta Carinae represents a stellar merger event in progress, two massive stars spiraling inward through gravitational wave radiation. The Advanced Laser Interferometer Gravitational Wave Observatory has detected no gravitational wave signatures from the system, despite theoretical models predicting detectable emissions from objects of this mass at this distance. Alternative theories propose that one component is a primordial black hole accreting matter from its stellar companion, but X-ray spectroscopy shows none of the characteristic signatures of black hole accretion disks. The gamma-ray burst potential creates scenarios that astronomical models cannot adequately address. If Eta Carinae produces a hypernova explosion, the resulting gamma-ray burst would deliver radiation equivalent to 100,000 years of solar energy to Earth's atmosphere within 10 seconds. Atmospheric chemistry models published in the Proceedings of the National Academy of Sciences suggest that such an event would deplete Earth's ozone layer by 90%, allowing lethal ultraviolet radiation to sterilize the planet's surface. The system's rotational axis appears aligned within 30 degrees of Earth's position, placing our planet directly in the potential gamma-ray burst cone. Why does the universe allow stars to exist beyond their theoretical mass limits? How can binary systems sustain energy outputs that exceed galactic luminosities? What mechanism prevents immediate gravitational collapse when radiation pressure should tear these objects apart? Could stellar remnants from the universe's first generation still lurk within modern star-forming regions? If Eta Carinae explodes tomorrow, would Earth's biosphere survive the sterilization event? The cosmos holds its most destructive forces in plain sight, burning across impossible distances, waiting for gravity to complete calculations that began when the universe was young. 10 events, 10 different scales of annihilation, from the quantum foam that might be unstable beneath our feet to the supermassive black hole that anchors our galaxy. From stellar explosions 25,000 light years away to magnetic field reversals happening in our planet's core right now, each represents a different failure mode for everything we know. Each suggests that the universe operates on principles we have barely begun to grasp. What emerges from these cosmic threats is not just the fragility of Earth, but the inadequacy of our models themselves. We build frameworks to contain infinity. We write equations to predict chaos. We map the local structure of space-time while swimming inside a bubble carved by ancient supernovas. We measure the rotation of Sagittarius A star while our own magnetic field weakens in ways we cannot explain. The standard model of particle physics suggests our vacuum state might be fundamentally unstable. The standard model of stellar evolution cannot account for why some stars explode early while others refuse to die on schedule. The standard model of planetary protection assumes we can catalog every asteroid, predict every coronal mass ejection, monitor every gamma ray burst in a universe that contains 400 billion galaxies we will never see. Here's what these 10 events reveal. The universe does not care about our categories. It operates on scales that make human civilization a statistical error. It generates energies that dwarf our sun while hiding in quantum states smaller than atomic nuclei. It builds structures millions of light years across while depending on forces we discovered decades ago and still do not understand. Every protective barrier we imagine around Earth exists at the mercy of processes that were ancient when our solar system was dust. The local bubble that shields us was carved by explosions that preceded complex life. The magnetic field that deflects solar wind is generated by a molten iron core we have never seen. The vacuum state that enables matter to exist might be a temporary aberration in a universe that prefers non-existence. We are not just vulnerable to cosmic events. We are cosmic events. Brief arrangements of matter surfing energy gradients in a universe that might erase us, not through malice, but through the simple act of returning to its ground state. The question is not whether these events will occur. The question is what they mean for any intelligence that believes it can predict them.